Welcome to Lecture 1.2, Linear Independence and Spanning Sets. Recall from last time the definition of a vector space. This consists of two things, a set V, think of these as vectors, and then a set F, which is a field, think of these as scalars. They're usually either real numbers or complex numbers, and then there's two conditions that have to hold. V has to be closed under addition, meaning if you add together any two vectors, you get another vector. And closed under scalar multiplication, which means if you take any vector and any scalar and you multiply them together, you get another vector. In general, we are not allowed to multiply vectors, though in sometimes there is a natural way to do that. That's generally not allowed in an arbitrary vector space. Here's a new definition for this time. A set S of V, so a set of vectors, is linearly independent if for any finite collection in that set, V1 up to Vn, this condition holds. So I'm going to call this henceforth a linear combination of the VI's. So if A1 V1 plus ... AN Vn equals 0, if that can only happen when all of the coefficients are equal to 0. That's what it means to be linearly independent. If S is not linearly independent, then we say it is linearly dependent. Sometimes we drop the word linearly from both of these for brevity and just say independent or dependent. Let's do some examples. I'll do an example followed by a non-example. So let's first take, say V is equal to R2, and let me take V1 to be the vector 1, 0, and V2 to be the vector 0, 1. So here's what this looks like visually. So let's say that if this is V1 and this is V2, then you can think of these two vectors as determining a grid. And we're going to come back to this example, or examples like this later, this grid example. So every point on this grid, or even in between this grid, can be expressed uniquely as some number of V1s and some number of V2s. Well, it turns out that it's unique, but it's not always the case. It turns out that's only the case if our set is independent. So let's try to understand this. So here's a point right here. Let me call this V. That is 3 V1s and 2 V2s. So that's 3 times V1 plus 2 times V2. And as I said, this doesn't have to be on a lattice point. This can be in between, and it could be like 1.5 V1s and 1.5 V2s. Or it could even have irrational coefficients. The coefficients have to come from the set of scalars. So why is this set independent? So if I try to write A1 times V1, that's 1, 0, plus A2 times V2, that's 0, 1. And so we can simplify that. We can write that as A1 and A2, and we can try to set that equal to 0. So independent means if an arbitrary linear combination of those vectors is equal to 0, then all of the coefficients must be equal to 0. So here's an arbitrary linear combination of these two vectors, and that's equal to A1 and A2. You set that equal to 0, 0, and you get right away that A1 has to be 0 and A2 has to be 0. So A1 is 0, A2 is 0. Geometrically, that means that the only way to end up at the 0 vector, the origin, from the origin, is to not move at all. So, in other words, if you move in any direction, positive or negative direction, in the V1 direction and the V2 direction, you're never going to end up at 0. So let's do a non-example now. Let me do this. Let me now take V1 and V2 as the same, and then let me take V3 to be 1, 1. So now I claim this is a linearly dependent set. And so how do we show that? We have to show that there is some non-trivial linear combination of these three vectors that gives the 0 vector. In other words, we have to say something times v1. So something times v1 plus something times v2 plus something times v3 equals 0, 0. Can we find coefficients a1, a2, and a3 so this linear combination is equal to 0? Take a moment to look at it, and you should realize that there's a lot of ways to do this. If you take one of these plus one of these and negative one of these, you add those up, you get 0. So the graphical, or the geometric way to think of this is, now you have the grid as I don't know if I'm going to be able to draw this very well. You have the same grid as before, where you can go horizontally and vertically, but now you also have a third vector. So this is v3, and that allows you to go in this direction. So in other words, if you start at the origin and you go one step that way, one step that way, and then negative one steps that way, you get back to 0. So this set is linearly independent, and this set is linearly dependent. Here's some intuition for the concept of linear independence that's not built into the definition, but it's not too hard to show that this is equivalent. So a subset of vectors is linearly independent if none of the vectors in S can be expressed as a linear combination of the others. So in our previous example, we had two vectors, v1 and v2. So let's write those down again, v1 and v2. There is no way to write either of these vectors as a linear combination of the others. That's just not possible. But if we have v3 is equal to 1, 1, now it is possible. Now I can write v3 using the other vectors. So in particular, I could write v3 as, let's try this again, something times 1, 0 plus something else times 0, 1. It's not hard to see that if you put a 1 there and a 1 there, that does the trick. So again, this is not the definition of what it means to be linearly independent or dependent, but it turns out that it is equivalent. Let's do some more examples. Consider the vector space R3. We'll look at a variety of sets S and see which are independent and which are not. First, let's consider a set containing a single vector v1, and I claim that is linearly independent if and only if v1 is non-zero. Now, let me say a few words about this. First of all, this IFF, that means if and only if. Sometimes that is written instead of IFF with this double arrow, like this. So what that means is, well, you write these two statements. I'm going to call this statement A and this statement B. And A is true if and only if B is true. That means, so we write that as A if and only if B. And that means if A is true, then B is true. And if B is true, then A is true. That's why we say if and only if. So what does it mean when I say this set is independent if and only if v1 is 0? Well, that means if this single set is independent, so if v1 is linearly independent, then v1 is non-zero, and conversely, if v1 is non-zero, then this set containing just v1 is linearly independent. And without writing much down, let's verify why this is true. So we have to use the definition up here. So if this set is linearly independent, then what does that mean? That means that a1 v1 is 0 can only happen if a1 equals 0. And that absolutely implies that v1 must be non-zero. Because if v1 is 0, then A1 doesn't have to be 0 for this product to be the 0 vector. So this direction checks out. Let's check the other direction. If V1 is equal to 0, well, then what? Then A1, V1, the only way to get a 0 vector from a constant times a non-zero vector is if that constant is 0. So then absolutely A1 has to be 0. So that statement checks out as well. So sometimes we say that V1 being non-zero is a necessary and sufficient condition for the set S to be linearly independent. Next, consider a set S containing two vectors in R3. So I claim that this set is linearly independent if and only if these two vectors do not lie on the same line. So I'm only going to draw 2 dimensions instead of 3 dimensions, just because it's easier. But let me draw 2 vectors. So say this is V1 and say this is V2. So these do not lie in the same line. And then an example of 2 vectors that do lie in the same line. Let me draw that line. Oops, that's supposed to go through the origin. Let's pretend it does. So here's V1, and so here's V2. Or maybe V2 is in the negative direction, or it could even be 0. So convince yourself, and when I say this, I mean I want you to make sure you understand this before moving on. Pause the lecture if you need to. Why this set of vectors is always linearly independent if they don't lie on the same line, and why this set of vectors is linearly dependent because they lie on the same line. So again, the set is linearly independent if and only if these vectors do not lie on the same line. Sometimes we say they are not collinear. The third example, a set S of 3 vectors in R3 is linearly independent if and only if those vectors do not lie on the same plane. Now, this is similar to an example that we saw a few slides ago where I had V1 was 1, 0, and V2 was 0, 1, and V3 was 1, 1. Remember, this was a linearly dependent set. The same thing holds in, say, in 3 dimensions. If you have any sort of plane, and now a plane is determined by 2 vectors, let's say V1 and V2. So those vectors determine the plane, and then the third vector, V3, if that vector lies on that plane, then it can be written as a linear combination of V1 and V2, meaning that we can write the 0 vector using V1, V2, and V3. However, if that vector lies off the plane, let's say it's like that, V3, then this set of 3 vectors is linearly independent. So again, this is an if and only if statement. Finally, a set S of 4 vectors is never linearly independent in 3-dimensional space. And one way to see that intuitively, I'm not going to prove it, but let's draw a picture to convince ourselves why this is true. If you take V1 and then V2, and these are not on the same line, then that determines a plane. So every vector on this plane I can write using V1 and V2. And then if I take a vector V3 that is not on this plane, now that is going to determine 3-dimensional space. We'll say it spans R3. That's a terminology that we will introduce later in this lecture. But the way to think of this is every vector in R3 can be written using V1, V2, and V3. So now it doesn't matter where you put R4. Put that vector anywhere you want to. You can write instead of R4, let me say V4. You can write V4 using V1, V2, and V3. So you can write V4 as, some A1 V1 plus A2 V2 plus A3 V3. So why is this set of 4 vectors linearly dependent? Well, because this condition here fails. there is a way to write the 0 vector non-trivially using these 4 vectors. And you should be able to see how to do it right here. Notice that a1 v1 plus a2 v2 plus a3 v3 minus v4, in this case, that is indeed equal to 0 for this particular choice of a1, a2, and a3. Therefore, this set of 4 vectors is always linearly dependent. Let's do some examples involving polynomials. Let's let V be the vector space of polynomials of degree at most 3, and consider the following subsets S. First, let's consider the set S containing 1, x, and x squared. I claim that is linearly independent. Well, let's try to see why. Let's take these 3 vectors, they're polynomials, but let's try to write the 0 vector using them. So something times 1 plus something times x plus something times x squared equals 0. There's only one way to do that. The only way that that's going to work is if you put a 0 there, a 0 here, and a 0 there. So that's exactly what it means for these 3 vectors to be linearly independent. Notice this is a slightly different notation as my definition up here, but it says exactly the same thing. Next, the set S containing 1, x, x squared, and x cubed is linearly independent for the same reason. Namely, if you try to take a linear combination of these 4 elements, let's try it, a naught times 1 plus a1 times x plus a2 times x squared plus a3 times x cubed, and try to write the 0 polynomial using those, there's only one way to do it. You have to have these coefficients equal to 0. Otherwise, this polynomial, well, it may have some roots. It may be 0 in a few places, but it's not going to be the 0 polynomial. This polynomial is 0 everywhere. It's identically 0. So this can only happen if a naught and a1 and a2 and a3 are all 0. Therefore, this set is linearly independent. Next, the following set containing 1, x, x squared, and 1 plus 3x minus 4x squared is linearly dependent. So to show this is true, you have to show that this implication up here fails, meaning you have to produce a way to write the 0 vector, or the 0 polynomial, using these 4 elements. And we can do that. Notice if you take negative 1 of these, negative 3 of these, and positive 4 of these, and you add those up, that's going to cancel with this. So explicitly, if I take negative 1, well, let me write that a little bit differently. How about this? I'm going to write that as blank times 1 plus blank times x plus blank times x squared plus blank times 1 plus 3x minus 4x squared equals 0. How do I fill in the blanks to get the 0 polynomial? Well, let's put a 1 there. Well, first of all, there's many ways to do that. I could have put a 10 right there, but let's put a 1 there. And if we do that, then that forces us to put a negative 1 there, a negative 1 there, a negative 3 there, and a negative 4 right there. So here is a linear combination of these 4 elements that gives the 0 polynomial. Finally, the following set, 1, x, x squared, and x cubed plus x plus 1, is indeed linearly independent. Now this probably isn't obvious right away, but we'll check it the same way that we did the previous examples. We'll try to write a linear combination, so something times 1 plus something times x plus something times x squared plus something times x cubed plus x plus 1 equals 0. So how do we get a linear combination of this to be 0? And remember, what is 0? 0 is 0 plus 0x plus 0x squared plus 0x cubed. So we are looking for things to put in these blanks so the coefficients are always 0. So notice, because we have a 0x cubed here, and we only have an x cubed here, that this coefficient has to be 0. So that is forced, because we need the x cubed coefficient to be 0. But now we also need the x squared coefficient to be 0, and that means that this thing has to be 0 as well. So we got to put a 0 there. And now we need the x coefficient to be 0, and there's only one option for this blank. That has to be 0. And similarly, this has to be 0. So we have shown directly that this set of 4 vectors or elements is linearly independent. Now you may be wondering, is there a more general way to do this? Because I could have given you a much harder example. I could have given you these two polynomials, like 1 plus 3x minus 4x squared. I can give you 4 polynomials that look something like this, and it's not at all clear, if you do the same process, whether there's going to be a set of 4 non-zero numbers that gives you the 0 vector or not. And so the answer is yes, there are algorithmic ways to do this, and they are fairly basic. They are taught in any linear algebra course, which often, I think a lot of you, if you're watching this lecture, you've seen this before. Basically, you take a matrix and you put the coefficients in rows of the matrix, and you do a little process called row reduction, and you see what you get, and you get a definite yes or no answer. It's not hard, but it is a little bit beyond the scope of this course, so we won't teach it. But if you are interested, I encourage you to maybe do a Google search or to pick up your favorite linear algebra textbook and teach yourself how to do this. Our third example involves the vector space of smooth functions, and let's look at complex valued functions for reasons that will become clear shortly. First, I claim that the set containing cosine of t and sine t is linearly independent. And the reason is because if you take a linear combination of these, c1 cosine of t plus c2 sine of t, the only way you're going to get the 0 function is if c1 and c2 are both equal to 0. Next, the set S containing e to the 2t and e to the 3t is linearly independent for the same reason. If you take a linear combination of those two functions, c1 e to the 2t plus c2 e to the 3t, the only way you're going to get 0 is if both c1 and c2 are equal to 0. Next, this set of 3 functions, e to the 2it, e to the negative 2it, and cosine of 2t, is actually linearly dependent. And the reason is because cosine of 2t can be written as 1/2 e to the 2it plus 1/2 e to the minus 2it. I assume this is something that you've seen in your mathematical studies so far, but it's possible that it hasn't come up. So if it hasn't, this holds not just for 2, but for any value of k. And now this is not the definition of being linearly dependent, but it's easy from here to say that, therefore, we can write a linear combination of these 3 functions. I think you see how to do it. Say 1/2 times e to the 2it plus 1/2 e to the minus 2it minus 1 times cosine of 2t to get the 0 function. Finally, this is a similar example. This is something that is probably more likely that you have not seen. E to the 2t, e to the minus 2t, and cosh, this is the hyperbolic cosine of 2t, is linearly dependent, and it's for almost the same reason. Cosh of 2t is 1/2 e to the 2t plus 1/2 e to the minus 2t. Notice that the formulas for cosine and cosh are very similar, and that is because, in general, if I take cosh of I times, say, theta, that is equal to cosine of theta. So this is how cosh and cosine are related. Now we come to our second big definition of this lecture. A subset S of a vector space V spans the space if every vector in the space can be written as a linear combination of things in S. So think of the word span as meaning generate. Moreover, If S is also linearly independent, then we say it is a basis of V. Here's a good way to think of things. If S spans V, that just means that S is big enough that it generates all of V. However, if S is a basis for V, well, that means that it generates V, but it's also a minimal set that generates V. When I say minimal, I mean there's nothing you can remove from S to preserve the property that it generates V. So all of those vectors are needed. Let's do some examples in the vector space R2. So here's one that we've seen before, 1, 0, and 0, 1. Recall, it makes no difference if we write it this way using ordered pairs or if we write them vertically like this. We usually prefer this way when we handwrite things, and when we write it out in lines of mathematical text, it's more convenient. It fits better if we write them with ordered pairs. But I claim that this spans R2. And the way to see it is if you take an arbitrary vector in R2, let's call it AB, then we can write that vector as linear combinations of V1 and V2, or as a linear combination, namely A times 1, 0 plus B times 0, 1. So yes, this indeed spans R2. Now, is it a basis? Well, we've already established that this is an independent set, and to be a basis, it just has to span and be independent. So this also is a basis. Now let's go back to our intuitive definition. It says a basis if it generates V, but it's a minimal set that generates. And so yes, this set here generates R2, but it's minimal in the sense that if we remove either of these vectors, it's not going to generate. Next, the set containing 3, 1 and 1, 0. 1, 1. So here's a picture of that. So let's say that 3, 1 is going to look like is that vector, and 1, 1 might be that one. So let's call this V1 and V2. Now, geometrically, hopefully it's clear why this spans, because these determine a grid, and every single vector in R2 lies somewhere in this grid, or in the interior. So this vector here, we can write as maybe 2/3 V1 and 2.5 V2. So this is 2/3 V1 plus, what did I say, 1.5? I actually mean 2.5, so say 5/2 V2, because it's 2/3 steps in this direction and 5/2 steps in that direction. So yes, this spans R2. Now if you want to be more formal about this, or more algebraic, what does it mean to span? That means any vector A, B can be written as some number C1 of 3, 1 and some number C2 of 1, 1. So it spans if you can, for a fixed A and B, if you can always find a C1 and C2, that works. So this just says, can you solve the following system of equations? So this is 3C1 plus C2 equals A, and C1 plus C2 equals B. And for any fixed A and B, so these things are fixed, you can always find a C1 and C2. That makes this work. So yes, this spans R2. Now, is it a basis? Is this linearly independent? The answer is yes. These vectors are not collinear. They do not lie in the same line. So this is a basis. And hopefully you can see, going back to our intuitive definition, that these guys span R2, but they minimally span R2. If you remove either V1 or V2, the grid goes away and you no longer generate all of R2. So our third example is if you start from this set and you add a vector. No, actually it's different. Never mind. It's if you start from this set and you add 3, 1. Does this span R2? And the answer is yes, because these two vectors alone are enough to generate R2, or to span, so throwing in a third one doesn't spoil the party. So this spans R2, but is it a basis? The answer to that is no, because this is not a linearly independent set. This guy is not needed. 3, 1 can be written as a linear combination of 1, 0 and 0, 1. So while this set generates V, it's not a minimal set that generates V. We can remove any of these 3 vectors and it will still generate. So is it a basis? No. And our last example is the singleton set 1, 1. So this, geometrically, it lies right here. It spans a subspace. It spans a line. It generates this line. But it will not generate R2. So it does not span R2. And because it does not span, it cannot be a basis. Here's a nice theorem that ties together the concepts of a basis, spanning set, and a linearly independent set. So let S be a collection of vectors in a vector space V. The following 3 things are all equivalent. First of all, S is a basis of V. S is a minimal spanning set of V. We talked about that on the previous slide. So this is a set that spans V, but it's a minimal set, and that if you remove anything, you destroy that property. Finally, S is a maximal linearly independent set in V. So S is linearly independent, but if you include any other vector with S, it destroys this property. There's going to be something that is redundant. So think of this as like a Goldilocks theorem. So S is a basis if and only if, it's big enough that it generates V, but it's not too big because nothing in the set is redundant or unnecessary. I'm not going to prove this theorem. I encourage you to try it on your own if you're so motivated. It's the sort of thing that you'll see in an advanced linear algebra course. Instead of a proof, I'll provide some motivation by going to maybe our favorite vector space R3. This is big enough that it's more interesting than R2, but it's small enough that we can actually draw it on paper and visualize it. So let's let V be the vector space R3, and let W be any plane through the origin in R3. And we want to ask, what is a basis of W? So you know from vector calculus that we need 2 vectors that are not collinear to generate or to span W. Moreover, any set of 2 vectors, V1 and V2, will do the trick. Any set of vectors I claim is a basis as long as they're not collinear. Well, because 2 non-collinear vectors will generate or span W, and they do so minimally. If you remove any one of those 2, you no longer get the whole plane. So it's a basis. Let's go up a dimension and find a basis for the whole vector space, V3. In fact, if you have any 3 vectors, I claim that that is a basis for V if and only if they are not coplanar. Now let's convince ourselves of this. Well, we've seen pictures like this earlier in the lecture. If you have V1 and V2 that are not collinear, then they generate this plane, or they span the plane. And if we have V3 that lies on the plane, then we still span the plane. So if V3 lies on the plane, it will not span the entire space. But once we get a V3 that does not lie on the plane, then it spans R3, and it's linearly independent, as we discussed earlier, and therefore it is a basis. It should be clear how this generalizes to higher dimensions, both in the case when your vector space is Rn, for n larger than 3, and the cases when W is a subspace of 1 or 2 or even higher dimensions as well. By the way, I said dimensions. What do we really mean by the word dimension? We haven't defined that, but we do have an intuitive picture as to what that should mean. Here's a formal definition. The dimension of a vector space is the number of vectors in any basis. Now, I call this a definition, but I should really call it a definition/theorem, because it's not at all clear that any two bases of a vector space have the same number of vectors in them. But that's something that can be proven, and again, it is proven in an advanced linear algebra course. But for our purposes, we will take it as a fact. So this is the definition of the dimension of a vector space. Let's do some examples. First, the dimension of Rn is not surprisingly equal to n. Now, there are many bases of Rn. They all have n vectors in them. Here's the simplest one, e1 up to en. Now, ei, in this case, is the vector of all zeros except in the ith place. So ith place. And here I don't need to put a hat here. Sometimes I just do it for emphasis. It's like sometimes I write a vector in boldface, other times I don't. So for example, in R3, this basis consists of 1, 0, 0, 0, 1, 0, and 0, 0, 1. And you can extend this definition for whatever Rn you happen to be in. Next, the dimension of the space of polynomials of degree at most n is n plus 1. And here's a basis, 1x, x squared, all the way up to xn, or x to the n. Now, obviously, there's many other possible bases, but this is the most canonical one. The dimension of the space of all polynomials is infinite. You need all powers of x to form a basis for this. And as I said before, as in the other examples, there's many other bases, but this is the most canonical. And finally, the dimension of the space of 2π periodic functions is also infinite. This shouldn't be a surprise, but what is a surprise is what a basis for this space actually is. So it turns out that a basis for the space of 2π periodic functions can be formed by taking all of the cosines and all of the sines like this. And that's an amazing fact. That's not trivial, but it really forms the basis, well, no pun intended, of a Fourier series, which is a big topic that we will study later in the class. So here's what this looks like visually. So let me try to draw this off. This is pi, this is 2π. So the function 1 is a constant. Cosine of x looks like this. Pardon my artwork in advance. Cosine of 2x looks like this. Cosine of, that's all I'm going to try to draw. I think the sines, for some reason, seem to be easier. Sine of x is looks like this. Sine of 2x is going to be like this. Sine of 3x and so forth. But it's an amazing fact that these form a basis, which means every single 2π periodic function, think about this for a moment, that's piecewise. It might be a square wave. It might be a triangle wave. It might be something else. It might be something like this thing. If it repeats every 2π, then this thing can be written uniquely as an potentially infinite sum of these sines and cosines. So for example, this square wave can be written as some constant plus some potentially infinite sum of cosines, let's say an cosine of nx plus bn sine of nx. And that's really a remarkable fact that, well, any musician can tell you that a sound wave can be decomposed into these fundamental frequencies. But mathematically, I think it's remarkable. Now, you may be having a few questions saying, well, I cheated a few times here. I mean, I have no longer, previously, I did not allow infinite sums. But here I am. So yes, I did cheat. There are some technicalities that I have swept under the rug, including these discontinuities here. But those are things that can be resolved, and we will return to them later in the class when we study Fourier series. This is an incredible topic, and it's extremely important for most of the material that we will see throughout this class. One quick remark is that any subset S of a vector space spans some subspace W. And we're going to denote this subspace by the span of S. So this is an important notational thing that we're going to use throughout the class. And so S can be a finite set. It could be an infinite set. Like, for example, if you take in R3, if you take, say, this half plane, take the xy plane where the y coordinate is positive, and so forth, that's an infinite set of vectors, but it spans a subspace. If you take all these things and see what they generate, it will in fact generate the entire plane as well, because you can, once you have a vector in here, you can take its negative and so forth. You clearly don't get anything out of this plane. You don't get any vectors that, say, point upwards. We'll conclude this lecture with an algorithm of how to construct a basis from any finite subset that spans a subspace. So let's let S be a finite set, and let W be the subspace that spans. So here's an example of what you might want to have in mind. So let's suppose that S contains these 5 vectors, say v1, v2, v5. Suppose these 5 vectors span this plane, W. So we want to construct a basis from this set. So essentially what we're going to do is we're going to remove elements from here until we get a basis. But we have to be careful because we can't necessarily just do that blindly and have it work out. So we first ask, is S actually a basis for W? If so, we're done. If not, then S is a spanning set, but it's not a minimal spanning set. That means we remove some vector v1 to get a smaller set that spans W. Now, let's be careful. That does not mean that we can remove any of the vi's. Like, for example, let's go down here and suppose v1 and v2 lie on the x-axis and v3 lies on the y-axis in R2. Now, v1, v2, and v3, these are not linearly independent because it's a spanning set, but it's not minimal. So why is it not minimal? Well, because we can remove v1 and these guys will still span. This is R2. Sorry about that. However, we can't just remove any of these. We can't remove v3. You see that? If we remove v3, then we no longer get a spanning set. So I can't just remove an arbitrary vi, but this just says that there is some vi or some v1 that we can remove to get a smaller spanning set. So let's do that. Now we ask again, is this new set S prime, is that a basis for W? If not, then we can remove some v2 from this. And I'm calling it v2, but it might not be v2, it might be v3. I'm just going to say we can renumber it if it's not actually v2. So there is some vector, let's call it v2, that we can remove from it to get a smaller set, S double prime, that spans W. Now, since S is a finite set, this process will eventually terminate, and we'll be left with a set, let's call it Sk, let's call it B, the kth iteration of this, which is a basis for W. Now, a key point here is that S is finite. If we had an infinite set, and you keep removing elements, you won't necessarily ever terminate. Like, suppose your set is countable or uncountable. Maybe it's the real numbers. You can't just keep removing real numbers and ever expect that that's going to terminate. And that involves properties of infinity, which I won't even get into. So if you've never seen that before, don't worry about it. Just know that this algorithm works because our set is finite. Let's do an example. So here's a set of 4 vectors in R3. Now right away we know that this is not a basis of anything because it's not linearly independent. So let's see what space this spans. So notice that the z-coordinate in all 4 of these vectors is 0. So in fact, these 4 vectors span the xy plane. We write this as span of S is a plane. Let's call that W. And since the plane is 2-dimensional, then any basis of W has 2 vectors. So what can we remove? There's many options, but if we want to, we can remove 1, 1, 0 and 3, 1, 0, and we're left with a basis of W, namely 1, 0, 0 and 0, 1, 0. This means that W, or the xy plane, is the set of all vectors of the following form: C1 times 1, 0, 0 plus C2 times 0, 1, 0, where C1 and C2 are arbitrary real numbers. In other words, every vector in W can be written uniquely like something like that. Now, if I want to, I can combine these vectors into one and write this as follows. I can just add these vectors and write this as C1, C2, 0, where C1 and C2 are real numbers. Now, this is not the only basis of the xy plane that we could have chosen from here. We could have instead removed, say, these two guys and gotten a basis. Now, you can't always remove any subset of size 2, but in this case, it turns out we can. But if we had done that, then let's see what this formula would have looked like. Then the xy plane is the set of all vectors of the following form: 1, 0, 0, and 3, 1, 0. So that means an arbitrary vector in the xy plane can be written like this: C1 plus 3, C2, C2, and 0, where C1 and C2 are arbitrary real numbers. Now, this set looks different than this. We say they have different parameterizations, but in fact, if you look at over all C1 and C2, these as sets are equal. Both of them are the xy plane.